Okay, so some of people rather back on knowledge science, and today we are going to talk about Cavalier's principle. Cavalier, and also we are going to talk about napkin rings for the example. Napkin rings is a bizarre shape. You have to core a sphere, and you'll get a napkin ring. Core a sphere and remove a cylinder from it, you get a napkin ring. So we are going to state the Cavalier's principle that two napkin rings with the same height, regardless of how big they are and how big the sphere is cut out from, it always states that it has the same volume. So let's call the height of the napkin ring h, and the sphere's radius, it's cut out from capital R. So let's draw a line straight out to the corner of the cylinder, down again. Here we have a right triangle. This is half the height of the napkin rings, and this, let's the radius of the cylinder. Nice small picture there. So the Pythagorean theorem states that this length, which is half the height of the cylinder, plus this length, which is the r, which is the radius of the cylinder, equals the hypotenuse square, which is the radius of the sphere itself. So we wind up with the radius of the cylinder squared plus half the height of the cylinder squared, equaling the radius of the cylinder, the sphere, which is the hypotenuse squared. So now now it's radius of the cylinder squared plus, equaling radius of the cylinder minus y squared, minus half the height of the cylinder squared. Let's take the square root of both sides. So these two things completely cancel out because we just subtracted h over 2 squared from both sides. So this square root and this completely cancel out. So we wind up with the radius of the cylinder equaling square root of radius of the sphere minus h over 2 squared. So this is what we need, is our formula. So now let's draw a line straight out to the corner of the cross section, back down. Here we have another right triangle. Let's call this height y, and this is the radius of the sphere itself. So the radius of the sphere squared plus y squared equals the radius of the sphere again. That's the radius of the sphere. So let's take the square root of radius. This again cancels out. So we wind up with something else. Okay. So we wind up with radius of the sphere equaling square root of r squared minus y squared. Yes. Now there is a way to describe a sphere's area. We need to subtract area of the cylinder from the sphere. So we have to take pi, multiply that squared minus pi. So the radii is probably taking this square root in each squared equation. This one with the square root in the squared equation, the behind one. So here is the square root of both of them. R squared minus h over 2 squared and r squared minus y squared. These two things completely cancel each other out because we are taking something and taking the square root of it and then squaring it. That just equals something irrational. So that just equals nothing anyways. So they cancel each other out. But what we are left with is what we need. We have pi r squared and we also have a negative pi y squared, negative pi r squared again, and a positive pi h over 2 squared. So we have pi r squared and a minus pi r squared. So they both cancel each other out. But what we are left with is what we need. Of course, y is bounded by the length of the sphere. So Cavalier's principle states that two napkin rings have the same volume regardless of the size of the sphere it's cut out from or the size of the napkin ring or the thickness. So it solves our thing and so subscribe to my channel if you want some more mind-bending math and other stuff and other things. So bye.